Now let's go into quantifying runtime. And to do this, we're really going to analyze the third option because that's what's mostly accepted in computer science today, and it's called big theta notation. So big theta notation is the runtime of a function in terms of n. And big theta only cares about large n, and it also chooses a cost model. So some operations we can basically enumerate. So it's important to understand that picking a cost model is not a simple task sometimes. We have to be very careful with what we use to get the right efficiency really. So one thing we don't want to do, notice that I didn't even define the return statement as a cost model because the return statement is kind of trivial. Once you return the function, it's done. So why would you even count that? There's no way to enumerate it. So a cost model is something you can enumerate and see how this enumeration occurs as the input size increases. So, and remember, because computer programs are meant to scale, we only really care about large n, because at the end of the day, a computer program can execute small scale programs extremely fast. So, but when we go into things like for example, Google as a company, it has billions of users. When someone enters a search, there may be billions of other searches happening at the same time. So how does it manage all of this? So that's when Google has to really think about the efficiency of its programs, because its programs are being used by billions of people, and that's a huge scalability thing. And I bet you they talk about big theta notation and runtime all the time because they have to think about that type of efficiency to get programs that we can even use. Because if Google is slow, no one would use it. And Google is so successful because their search algorithm is extremely fast and gets the correct results. So efficiency is so important, especially when we look at scalability. And that's why this third option is so good, because it shows the way that the algorithm and any algorithm or program scales as and increases. So because of that, so for in the case of something with the runtime of n, we know that if we have a billion users, it's going to take about a billion operations to do something. So that's why big data is very nice. But I'm going to talk more about big data and the mechanics of this soon. But basically, because we're only looking at large n, we're going to ignore constant factors and we're going to ignore lower order terms. So this should sound familiar. This was from our math problem, the easy method of the math problem. So this is why it's important, because in big data notation, if we figure out a function of the runtime, we're going to ignore constant factors and we're going to ignore lower order terms. So I'll give you an example of this. So before I go into an example of this though, let's give a formal definition for big data notation. So what it formally means, for any large n, the runtime of a function is going to equal theta of some function of n, okay? And n is the input size. Now, one thing that has to be true for this runtime is that it should give a tight bound for the runtime of the function. So formally what that means is there has to be some constants times this f of n that's less than or equal to the runtime, and also another constant times f of n that has to be greater than or equal to the runtime. So this is the formal definition of big data notation. So this can be a little confusing, so I will just go through an example of how this works. But to give you a visual idea of what this means, if we have some limits on the runtime, so the actual runtime of this function might look something like this. It's very erratic, but for large n, it has to be the case that big data defines something within two constant factors of the runtime. So it gives like a tight bound, so we have some level of accuracy. Because at the end of the day, defining runtime as such is a very big simplification, because there could be a lot of other factors going on. But because we're able to give a tight bound for it, we have a fairly accurate understanding of how the function works, especially when n becomes very large. Alright, so let's look at a trivial big data example. Let's say we had a cost model, and the function the function showed that the cost model resulted in operations of 2n plus 3 for all as a function of n. So what this means is that the runtime of this in big theta notation is theta of n. Now why is this true? Well, remember, runtime is theta of f of n, and what we're going to do is we're going to ignore constant factors and we're going to ignore lower order terms. So we ignore the constant factor 2 and we ignore the lower order term 3, so we get theta of n. Now, formally, what this means, if we look at the formal definition, we have the function 2n plus 3. It has to be the case that the runtime is greater than or equal to 0.25 times f of n, and less than or equal to 2 times f of n. Now, where did I get the 0.25 and 2? Well, I just arbitrarily picked that, so it works. So basically what big data says is that there has to exist some constants that this is true. If it exists, then the big data works. If it doesn't exist, then you can't use that big data as a function of that. So basically, this is true because if we use the distributed property and expand this, we know for large n is going to be greater than or equal to 0.5n plus 0.75, and for large n is going to be less than or equal to 4n plus 6. And this is always going to be true, so that basically means that this is a formal way to define the runtime of this function. So some common runtimes of programs that you'll see constant time, logarithmic time, linear arithmetic time, which is n log n, and quadratic time and exponential time. So I actually listed this in the order of which we prefer them. So constant time is obviously the best because that's the fastest. Now exponential time actually turns out to be terrible. Even the biggest computers in the world suck when it comes to exponential time. Like, they can't even handle exponential time. So it's important that we understand that exponential time is bad, and generally the other operations that are more polynomial are generally not that bad. And logarithmic time actually ends up being extremely fast. It's almost as good as constant time. So just to give you a broad overview of what runtime means. Okay, so now let's actually look at some examples of finding the runtime of a function. So now we've been doing some mathematical examples, so now let's look at some computer science examples. After all, this is a computer science course. But anyway, so in this example, which we've now analyzed, we found that the cost model was worst case n. So that means that the big theta notation of this is theta n. And just go over the previous slides if you didn't understand quite how we got there. But now let's look at another example. And for this one, I'm actually going to go into the editor, and we're going to diagram this out. So here we have the factorial function. So how are we going to figure out the runtime of the factorial function? And so the first step we have to do whenever we figure out runtime of something is we have to figure out a cost model. So first step is figure out cost model. Okay, and what's the cost? What cost model should we use for factorial? And it can be a little tricky, but when we have recursive functions, a good cost model generally is that we should use the how many calls recursively occurs. So in factorial, let's say, so what I like to do when I think of big data problems is I first try to think of specific cases of the problem. So just to give myself an understanding of how the function works. So let's look at n is equal to 5. So input is going to be 5, and let's see how many calls occur. So we're going to have factorial. So I'm just going to abbreviate to fact basically, and factorial 5 is going to then call fact of 4, which is then going to call factorial of 3, and this is going to call factorial of 2, and you get the idea. It's going to go all the way to factorial of 0. So how many function calls did we have? So this means that there were 6 calls when we had an input of 5. Okay, so now let's see just to get another example, what happens if we have an input of 10? So we're going to have factorial of 10, then factorial of 9, and then we're going to go all the way down to factorial of 0. So how many calls did we have? We had 11 calls. So notice that if my input is n, I can assume that the number of calls I'm going to have is going to be n plus 1. So this is our function in terms of the cost model. So what is this function in big theta notation? We ignore the lower order terms and we get theta of n. So this is a linear time function. This is a linear time function. So the runtime of this is theta n. Now, in the next example, we have this function g. So let's look at this and how this function works. So what we're going to do is, in this example, we're going to again figure out a cost model. And what I'm going to do is I'm going to count so my cost model is going to be, I'm going to define it as the bindings of I and j. And the reason I can do this is because the print function is just going to do something. I could count the number of times the print function is called, but I think figuring out the bindings of I and j will let me be able to organize this better. So let's say my input is 5 again. So let's analyze this. So what's first going to happen is it's going to go for I in range of 5. What's the first I value we get? We get I is equal to 0. And then when we have I is equal to 0, we're going to execute the inner for loop how many times? For j in range of 5. So when I is 0, we have j is equal to 0, then j is equal to 1, then j is equal to 2, all the way up to j is equal to 4. So this, for I equals 0 only, there's 5 calls. Means 5 bindings of I and j. So then after we finish j, we're going to get I equals 1, and we're going to get j equals 0 again, j equals 1, and then we're going to get j is equal to 4. And that's going to result in 5 bindings again. So now you might notice a pattern. So until how long are we going to go? So we're going to go until I is equal to 4. And then we're going to have the same pattern of j equals 0, j is equal to 1, all the way up to j is equal to 4. So how many bindings did we have in overall? We had 5 times 5, 20 bindings. 25 bindings. So for input 5. So already you might be able to notice a pattern in that if we have an input of n, we're going to end up with n times n bindings. And this is again the function of the cost model. So what this tells us is our big theta notation for this is going to be n squared. So this is a quadratic time function. So again, the best way to do big theta problems is to just look at examples and see how the function acts, and then see if you can get a broader generalization of that pattern.